How are we tonight? Can I tell a quick story? A little embarrassed. Who's seen the movie The Naked Gun? You remember that movie from the 80s? Leslie Nielsen? So I was handed this microphone and then immediately started to head into the bathroom and was quickly grabbed and stopped before I embarrassed myself and all of you with those sounds. My name's Scott Walter. I'm the, what am I, Summer? Outgoing executive director here at the Kickapoo Valley Reserve. For those that have seen me around for the last year plus, I've taken a part-time teaching job at UW-Platteville so I can help my wife more on our farm and to help her manage our seemingly exploding maple syrup business. So the board's working to refill my position, and maybe in the next month or two you'll see somebody else standing up here introducing our speakers. But always an exciting time of the month for me. These driftless dialogue talks bring experts with a wide range of experience to educate us and inform us about key issues surrounding natural resources here in the Kickapoo River Valley and beyond. And tonight's topic, no exception. When you think about the issues facing our groundwater systems, you're probably familiar and have heard about our karst geology here and the possible impacts of CAFOs that are in place and being planned, PFAS, those forever chemicals that have made headlines over the last couple of years. Big issues, I think, related to tonight's topic. So want to mention a couple things quickly. First, we always preface these by reading our KVR land acknowledgement statement. The Kickapoo Reserve Management Board acknowledges that the state and federal lands that comprise the reserve fall within the ancestral homelands of First Nations people, including the Ho-Chunk Nation. We recognize the sovereignty of the Ho-Chunk and other First Nations and will work towards a shared future by continuing to create collaborative opportunities to protect and preserve these lands. And then a quick introduction of tonight's speaker, and then I'll hand the microphone over to him. Dr. Kenneth Bradbury is Wisconsin's state geologist and director of the Wisconsin Geological and Natural History Survey in the UW-Madison Division of Extension. Ken is a hydrogeologist who has worked and published on groundwater issues in Wisconsin since 1982 with a focus on applied problems. His research has included investigations of virus transport in groundwater recharge processes, wetland protection, regional groundwater simulation, and the hydrogeology of glacial deposits. He received his bachelor's from Ohio Wesleyan University, where he majored in geology, then earned a master's from Indiana and a PhD from the UW-Madison Department of Geology in 1982. He's affiliate faculty member in the UW-Madison Department of Geoscience and the Nelson Institute at UW-Madison. He's a fellow in the Geological Society of America and is active in the Association of American State Geologists. These guys are so impressive every month. Ken has served on the Water Science and Technology Board of the National Academy of Sciences and on committees advising the U.S. Geological Survey. So I'll hand the microphone over to Ken. Why don't we give him a nice welcome?
Thank you. Well, thank you very much. What you didn't say and which wasn't updated is that I'm no longer the state geologist because I'm retired. I retired in July and I'm enjoying it quite a lot, but I get to do things like this tonight, so which kind of keeps me interested. So thank you all for showing up on such a beautiful evening and such a beautiful place. So this is a Badger Talk, and what's a Badger Talk? A Badger Talk is sponsored by the University of Wisconsin-Madison. It's part of their outreach effort to promote UW-Madison around the state. So they partially or totally fund the talks like this by various faculty experts. As I said, I'm no longer the state geologist. I'm retired, but I'm emeritus professor now. So anyway, a little bit about Badger Talks and outreach, the UW-Madison outreach program. But a lot of different topics they have. So if you guys ever want speakers, check out Badger Talks, because there's a whole, really hundreds of different topics that you can get. But tonight we're going to talk about groundwater. And as he pointed out, this is a big issue. And it's, I've only got, an hour or a little less here. I can't possibly get to any depth about any of the big issues, but I'm happy to answer questions at the end if we want to talk about anything in particular. What I'm going to do is give you just a brief word about what the Wisconsin Geological and Natural History Survey is. Then we'll start in about Wisconsin geology and how that affects our groundwater aquifers, how we use groundwater, groundwater quality, groundwater quantity, groundwater surface water interactions, and some recent groundwater policy and legal challenges and changes in Wisconsin. Okay, so who is the Wisconsin Geological and Natural History Survey that I used to direct but don't anymore? So this is a sort of a quasi-state agency that's been attached to the University of Wisconsin for many years, but it's similar to state geological surveys that just about every state in the union has. So our survey does research and resource evaluation on the rocks, water, and minerals of the state. And if you think about it, historically, we go back to 1853 when the state was young and the legislature wanted to know what we had. What did Wisconsin have as far as minerals and water resources, and did they have gold, and were there diamonds somewhere? So they sent survey parties out to map these things, and we're still doing it. Our current organization dates to 1897, and we're, as he said, we're part of the University of Wisconsin, UW-Madison Division of Extension these days. We have a staff of about 30 people. We have a nice website, and I wanted to point out that if you go to our website, wgnhs.wisc.edu, and there's a publications page there that has literally hundreds of, maybe 1,000 or more maps and publications, reports about the geology of the state that you can download for free and print out yourself. And it's really a fantastic, some of them go back over 100 years and some of them are brand new, but really a fantastic source of information for you. And a lot of other information about the state's geology on our webpage. So this is a talk about groundwater, just to get everybody on the same page. Groundwater is water under the ground, water that's filling the cracks, pores, cavities, caverns, interstices in the rocks and soil below our feet, below the Earth's surface. So that's groundwater. And just a little diagram here, a cross section of a soil zone and a water table, just so everyone's on the right framework here. So this is the land surface, and if you dig a hole at some point you hit water, and that's the water table. The water table is the surface of the part of the ground that's saturated with water. So below this line called the water table, all the pores and cracks are full of water, and so that's called the saturated zone. Above that point, there may be some moisture, but the pores are not full of water. So say the sand or soil or whatever, it may be moist, but it's not saturated. And we have something right above the water table called the capillary fringe, where water is pulled up by capillary pressure, just a few inches or so. So that's not a very critical thing to know, but that can actually be saturated and just above the water table, but that's really not important for us here. But just to understand, the water table is a surface. Below the water table, things are saturated. And recharge and precipitation and recharge are happening up the land surface, and some of that water infiltrates to become groundwater. That's through groundwater recharge. And so groundwater is filling all those pores, and then we have something called an aquifer. What is an aquifer? An aquifer is a geologic formation that can store or transmit usable quantities of water, of groundwater. So something like a sandstone or sand and gravel that's porous allows water to move through the pores at a rate that can be useful to people or to the environment. So here we have a typical Wisconsin landscape cross-section, and here we have two aquifers. We have a shallow sand and gravel maybe aquifer. We have this thing here called a confining layer, also called an aquitard, which might be like a shale or a clay. Below that we have another aquifer, and that might be sandstone in this case. And so both of these are transmitting water. You see the little blue lines are groundwater flow paths that are going from a recharge place up here where precipitation is entering the ground and infiltrating down and then moving along and discharging somewhere. All water starts as precipitation, snow or rain on the landscape. Most of that runs off to become surface water, but some percentage of it recharges depending on where you are and becomes groundwater. And so the top of this is called the water table, and then discharge happens to lakes or wetlands or rivers or to a well. So here's a well pumping and some of the water is getting pulled out of the well. So as we talk about aquifers, this is what we're talking about. Formations that allow water to flow through them. Now, usable quantities, anything below the surface can be saturated with water, but if it's a clay, it may not be holding enough water or transmitting enough water to be really useful. So we don't call that an aquifer. That might be an aquitard or a confining bed, but probably not an aquifer. So let's look at Wisconsin's geology now, and I know we're here in a beautiful part of western Wisconsin, but we're going to cover the whole state. Wisconsin has prolific aquifers over most of the state, and Wisconsin's geology influences groundwater availability. So the takeaway point here is groundwater conditions vary across the state because of our geology. So we'll have a very brief geology lesson now. Here is the simplified bedrock geology map of Wisconsin. This is what a very simple picture of our bedrock would look like if we stripped away all the sand and gravel and glacial deposits over the top. So each color represents a different type of rock or a different age of rock in this case. And our rocks are, one of the fascinating things about Wisconsin geology is we have some of the oldest rocks in the world, some of these Precambrian rocks that go back almost 3 billion years in age. And we have some of the youngest and greatest glacial deposits in the world that are only 10,000 years or so old. And so we stretch across the whole geologic time column. Unfortunately, we're missing parts of it. So we have what are called, we have Precambrian rocks, which are these very, very billion-year-old rocks. We have a lot of Paleozoic rocks, which are in the range of 300 to 500 million years old. And we have some Cenozoic and Quaternary deposits up here that are on just a few million years old, but we're missing a lot of the Mesozoic, Jurassic Park. We didn't have that. All those rocks either weren't deposited or they've been eroded away. Okay, so we span the geologic time scale, but we don't have all of it represented here. The other thing to note here is that we have a dome, a structural dome across Wisconsin. So if you sliced across Wisconsin here, and that's what we're showing here, there's these crystalline basement rocks, these that are brown here, form what's called the Wisconsin Dome. They're higher in the middle, and that would be the rocks that you would see up in north central Wisconsin. And then they slope off toward Lake Michigan and over toward Iowa and Minnesota. And so these younger rocks on top of them are either dipping to the east or dipping to the west. And we'll see more about that in a second here. So let's look at these rocks in a little more detail here. So in the north here, in these Precambrian rocks are crystalline rocks, like things like granite or quartzite that you might see up at the dells, the St. Croix dells. Most of the central part of the state were underlain by Cambrian sandstones that you might see at the Wisconsin dells. These nice cross-bedded sandstones. southwest Wisconsin here, we have sandstones, but we also have limestone and dolomites that are on top of this sandstone that would be here, and these rocks that would be dipping off to the west. And then if we go over to eastern Wisconsin, we have the Silurian dolomites, which are younger rocks, and they are dipping off to the east. And so these are the rocks you might see if you went up to around Door County, for example. And each of these can form a different type of aquifer. So the crystalline, what we call the crystalline aquifer, are these crystalline rocks in north central Wisconsin, things like granite or schist. Here you might see a picture of the dells of the Eau Claire River. They're not very porous. These rocks they're not porous rocks. They're hard crystalline rocks, don't have a lot of pore space, so groundwater has to occur to them in those rocks, in fractures in the rocks. So well yields in these rocks can be very, very low. So it's difficult in north central Wisconsin to get water out of rock. The well yields are low, and so they have to depend on shallow sand and gravel aquifers up there in many places, or get low yielding wells out of these crystalline rocks. If we move to most of the southern part of the state is underlain by these sandstones, again, like you might see in the Wisconsin Dells if you take the boat trip. This Cambrian, what we call the Cambrian sandstone aquifer, extends through southern and central Wisconsin, also goes down into Illinois, over into Iowa and Minnesota, where it's a very, very important aquifer for most of the high capacity wells in the state. So this is a very important aquifer, although we don't see it a lot of times because it's often below our feet. We can see it here at the Wisconsin Dells. And how did that form? Well, this Cambrian geology was a time of shallow seas in Wisconsin. So these sandstones formed either in a shallow kind of beach environment, or maybe above the waterline and with sand dunes where there was a lot of wind-blown sand. So these things that's why you see these features like cross-bedding and ripple marks in these formations. And so if we go to southern and southwest Wisconsin, there's a whole stratigraphy of these sandstones, and you hear the things called like the Waniwak Formation, the Mount Simon Sandstone, the Tunnel City or Lone Rock Formation. These are all the Jordan Sandstone. These are all different advances or retreats of ancient seas that deposited these things along shorelines. And there's a lot of great views of the sandstone aquifer. Here, if you go to Rockbridge, you can see this Cambrian sandstone. There's actually a little tunnel there you can walk inside. You can see this nice cross-bedding there. Under a microscope, this is a hydrogeologist's dream aquifer. This very rounded sand grains, very well sorted, meaning they're all about the same size. They're very clean, meaning there's not anything there except quartz sand. So this is a wonderful, wonderful aquifer, and that's why it's such a great aquifer for many of the high capacity wells, like the wells in Madison, the wells in Waukesha. They're all producing out of this sort of material. Now let's move over to west Wisconsin, right around here, or south of here, where things are a little more complicated, where we have this more of a layer cake stratigraphy. And if you look at this road cut on 151, 151, where you can see these different stratigraphic units being cut through there, and you can actually see groundwater seeping out along here where it's darker there, and that's because there are aquitards or shaly units within there that don't allow the water to percolate downward as rapidly. So this is a more complicated situation in southwestern Wisconsin, which makes it a little harder for hydrogeologists to figure out what's going on, and we'll talk more about that later. The other thing about southwestern Wisconsin is it's an older landscape, hasn't been glaciated, and so there was a lot of downcutting and incision of streams. And so this is an old diagram from a book by Wiedemann and Schultz from 1915. I thought I'd show it because it's just a nice cartoon of how these rivers, like the Kickapoo here, are cutting down through these different units. So we have the Cambrian sandstones and the Platteville Formation on top and the St. Peter Sandstone. You can see how the Kickapoo, this is the Richland Creek, and the Mississippi River have cut down through these units, and so have cut off these upper aquifers. And that's, we have this topography you can see right out the window here, which is different than in other parts of Wisconsin. So this is kind of a unique area that way. And here's just another view of the same thing. This is taken from an idea that you would see a little bit farther south, and we have more names for all these formations, and now like the Galena, the Decorah, the Platteville, the St. Peter, but these are all Cambrian units. The interesting thing here is we can have two different aquifers in this bedrock because we have a thin shale called the Glenwood Shale that's right above the St. Peter Sandstone here, and so you can have a groundwater up here. You might even have an unsaturated zone and then more groundwater here, and that's what I've been showing, what we're showing here with these. Think of these as two different wells, and so a shallow well might have a water sitting in the well at that level, and a well right next to it that's deeper, that goes below this Glenwood Shale, might have a lower water level, and so you can get some very complicated water levels in these formations around in southwest Wisconsin. We'll come back to southwest Wisconsin, but now let's move over to Lake Michigan and the Silurian Dolomite, a place where I've done a lot of work. These are the rocks that extend from the Illinois border up to the tip of Door County, and then they actually wrap around the Upper Peninsula and around the Michigan Basin. You can see them over at Niagara Falls. The same formation makes up Niagara Falls. This is the escarpment that Niagara Falls is falling over. This Silurian rock is a fractured rock. It's a very important aquifer in eastern Wisconsin. You see that it's here in our cross section. It's dipping off to the east, and so it's a rock that's not present in the west or other parts of the state, just present in eastern Wisconsin. Very vulnerable aquifer. A lot of contamination issues there because of the fractures and the lack of any significant soil cover over those rocks. And here, if you go to Peninsula State Park, you can see this big escarpment. This is called the Silurian or Niagara escarpment, and that's because that exists because as these rocks, this is a cross section across eastern Wisconsin that goes from up there to say around Shawano, where the Wolf River is, over toward Lake Michigan, and if we're in central Wisconsin, we have these Precambrian crystalline rocks near the surface. Farther east we go, we get into these Paleozoic, younger Cambrian, Ordovician, and Silurian rocks. You can see that they're all dipping out into what's called the Michigan Basin, or go out under Lake Michigan. And whenever you come to one of these subcrops, the erosion is going to cause this escarpment. And again, this is the same escarpment or cliff that wraps around Michigan and becomes Niagara Falls. And you can find this, you can trace that for hundreds of miles. So this marks the western boundary of this Silurian Dolomite aquifer. And this, as I said, is very fractured, and I've always thought it's fascinating. This is a photo that I took years ago from a small plane over an alfalfa field, and you can see, even though there's alfalfa growing and crops growing in this field, you can see this pattern of fractures in that dolomite that are caused by the fractures holding moisture and the alfalfa growing more vigorously there, alfalfa being a deep-rooted plant. And so the fracture pattern in the dolomite is expressed in the vegetation. And you can see why this would be a very vulnerable aquifer, because you've got all these fractures that are coming up very near the surface, and oftentimes you see things like this, a swallet opening up where you've got water draining right in. Now I know we have things like that in this part of the state as well, and I'll talk about those a little later. I like to give people a concept of depth. I think many people don't have a good depth idea of scale of geologic formations, and this slide is designed to do that. So this is Milwaukee, skyline of Milwaukee as viewed from a boat out in Lake Michigan. And this is all to scale. So, and this is a sort of a generalized view of the rock formations under Milwaukee, where we have the Silurian dolomite, we have a shale called the Maquoketa Shale, which is an aquitard, and then we have these Cambrian sandstones, and then we have this granite or these Precambrian rocks at depth. Now, the tallest building in Milwaukee is about 600 feet high, okay? And so, how deep is a domestic well? The typical well in Wisconsin is 100 to 300 feet deep, typical homeowner well. Some are deeper, of course, but you know, if you just had to average, I'd say 100 to 300. So about half as deep as the tallest building in Milwaukee. How about most municipal wells in Wisconsin are between 200 and 800 feet deep. So they are as deep or deeper than as the height of the tallest building in Milwaukee. So if you're in Milwaukee and you look up, you know, you think, well, that's, you know, to think about looking down and drilling a hole that deep. The deepest wells in the state, or deepest well I've ever found, was 2,200 feet deep. And that was over in Waukesha. Goes way down into the sandstone aquifer, so it's several times deeper than the tallest building in Milwaukee. Now, that well was drilled over 100 years ago. Now think of the infrastructure it took to drill a 2,200 foot deep well 100 years ago. You know, that's some big important engineering, and how much it costs. And now also think how much energy it takes to take the water from down here and pump it up to the top penthouse in that building. So there's not an inconsequential amount of energy that's needed to pump this water around. So just to guide some ideas of scale here. Now let's talk a little bit about glaciation. I've been talking about bedrock geology, but remember Wisconsin was glaciated in the Pleistocene. We had an ice sheets that came across the Midwest and covered lots of the Midwest, although it didn't cover all of Wisconsin because we have this area down here called the driftless area. We had these different ice lobes that came at different times. You know, you see pictures like this and you think, well, it's sort of a static thing, but in fact it wasn't. It was very dynamic. The ice was coming and going, and these lobes didn't all form at the same time, and they didn't all look like that at the same time. So this is just a snapshot in time, okay? But we did have a lot of ice here, and that part of that ice dammed up a lake here called Glacial Lake, Wisconsin, that was here for like 1,000 years. And what did that leave behind? Well, it left behind a lot of deposits, sand and gravel. And so that sand and gravel forms a really important aquifer. We call it the sand and gravel aquifer. And, you know, this gravel like this, it's over near West Bend. On this map, the yellow areas are areas where we have significant sand and gravel deposits. Now, I said northern Wisconsin, the bedrock is not terribly permeable because it's crystalline, but we also have a lot of sand and gravel up there, and so that's where shallow wells can be completed in this shallow aquifer up there. Southern Wisconsin, we have to look more along river valleys, like the Wisconsin River Valley or the Black River or the Chippewa River, or along the Mississippi, of course. And so these are important aquifers, and a very important one I'll talk about more is the Central Sands, where we have a lot of irrigation wells in this shallow sand and gravel aquifer, and that's causing some issues with groundwater use, but it's also a very important area for growing vegetables and other crops. So that sand and gravel aquifer is very important. Now let's talk about the driftless area, though, a little bit, which we're sitting in tonight. First of all, where is the driftless area? Well, most maps that you see show, this is a map of the glacial deposits of Wisconsin, an older map, and all these different colors are glacial deposits. Then you see kind of a blank area where there aren't any. That's generally called the driftless area. Here's another view of it, of these ice lobes. And so there was area here that was not glaciated. That's why we have these high hills and this rugged topography that we have out the window here, because it was not covered by ice. But there's always a little dispute about exactly where that is. And so my colleague Eric Carson, who, by the way, is now the interim state geologist, in case you're interested who's doing that now, came out with this book a couple of years ago that was based on a work of, it was in honor of Dr. Jim Knox, who was a rather well-known geomorphologist from UW-Madison. But this is all about the driftless area. So if you want to know about the geography and geology of the driftless area, this is the book to get. But I wanted to point out that the geologist's interpretation of the driftless area is just the area within this dark yellow line. Never glaciated. There's been fluvial incision of the bedrock to make these hills, and there aren't any glacial deposits or drift. Now, other maps that you will see take the driftless area out into Iowa and Minnesota and even up to central Wisconsin. The geologist's interpretation is this is not correct, that this has topography similar to the driftless area, but it also has drift. So it's not driftless, neither is the part in Minnesota, and neither is up here in central Wisconsin. So the geologist's definition of the driftless area is just this, which is mostly in Wisconsin and a little bit in Illinois. Now let's talk about how groundwater moves. Groundwater moves from higher to lower hydraulic head or higher to lower elevations. And so in a cartoon like this of a landscape, we've got groundwater moving from hilltops. In a humid climate like Wisconsin, we have groundwater moving from hilltops down toward low parts, which might be a stream. But it also moves in 3 dimensions. So if we pull that apart, we can see that groundwater is not only moving laterally across the landscape, but it's also moving down under the high parts of the landscape, and then it can actually move up toward a stream or a low point. And these lines here we call groundwater divides because groundwater is going to move in opposite directions on top of that divide. So that's important to realize because it means that groundwater over here isn't going to end up over here. It can only go that way unless we do something different, like we put a big well here and pump it and change the water table somehow. But under natural conditions, we use this topography and this understanding of groundwater flow to kind of map groundwater flow directions. And as you see, groundwater is converging on the stream and it's flowing upwards. So this is a place where we would see artesian wells and springs to appear. And so we always, in valleys like the Kickapoo Valley here, it's not uncommon to see flowing wells or springs. And I'll talk about artesian or flowing wells in just a minute. Of course, that was a cartoon. The real system is more complicated. And so here's a couple of diagrams, and these are from my colleagues at the Minnesota Geological Survey, right across the river. But they could be Wisconsin. We just would flip it the other way. But you can see here that we have these different formations. We've got water tables that are a little more complicated, and we can have springs and seeps along these escarpments. We can have, for instance, here we have a water table, and then we could have an unsaturated zone and a deeper water table. So it can be a little more complicated. And then here's an even more complicated example from my friend Tony Runkle at the Minnesota survey. The Minnesota's interpretation of these different aquifers and how, and the colors here represent different ages of water and how it's a complicated system here in southwest Wisconsin because we have these stacked aquifers and water of different ages and a lot of mixing going on. And then they came up with even a more complicated diagram, but again, fairly realistic of what they call the bluffland karst landscape. Again, it's really fairly accurate for right around here, even though this was taken from example from Minnesota, where you have some steep valleys, you have uplands, you have a fairly steep valleys, you have these different geologic units, you have water infiltrating through springs or through sinkholes and karst features and fractures up here. Some of it goes very deep. Some of it doesn't go very deep at all. So there's a mixture of old and young water down there. And then you have discharge down here in a stream. You have springs. You can have deep and shallow wells that have different water tables. So all these things that I've been talking about are present here. So a lot of different processes going on. So let's talk a little bit about groundwater, surface water interactions. In Wisconsin and in the Midwest, groundwater and surface water are really tightly linked. And so they really need to be talked about together. Groundwater and surface water are not separate things. They're both parts of the same water system, and you really can't separate them. And we know that, one way we know that is by looking at base flow and trout streams in Wisconsin. And here we are in an area of a lot of trout streams down here in western Wisconsin. But so this is a map of the base flow index for Wisconsin. Base flow is the groundwater flow that sustains streams like this trout stream, sustains it even in the dry summer. Those streams are flowing. It hasn't rained for a while, but they're still flowing. Why are they flowing? They're flowing because they're getting groundwater discharge. And that's what makes a good trout stream. Cold, steady flow is what you need for trout, and groundwater provides that. And so this is a map of DNR's trout streams, and then the colors on the map represent base flow percentage, and a blue is high and red is low. And so you can see where we have high base flow percentage, we have a lot of trout streams. And if you go areas like this, where there's not much base flow, you don't get trout streams. We don't get many trout streams in eastern Wisconsin. So base flow is really related to trout streams, and it's a good example of groundwater surface water interaction. And also springs. We have many springs in Wisconsin. A few years ago, some of my colleagues did an inventory of historical data and came up with over 10,000 mapped springs across the state. This is how they were distributed, and this came from old DNR, or what was called the Department of Conservation mapping that was done back in the 1950s and 1960s. It was a little uneven, so some counties, a lot of mapping was done and others not so much, but you get an idea that there are a lot of springs, and look how many are concentrated in western Wisconsin because of the driftless area and because of this high base flow index. Now that study was, there was additional work done just a few years ago where again, some colleagues of mine at the survey went out and actually mapped springs that had at least 0.25 cubic feet per second discharge, which is about 112 gallons per minute. That was chosen because that is that much water is what most people, I think, would say is a pretty nice looking spring. In other words, it's not just a damp spot on the ground. You can actually see some water movement, and it's something that you might want to protect. It's something that's good for wildlife and so forth. And so these are springs that they actually went out and measured and mapped. And you can see again that there's a large concentration of them in southwest Wisconsin. There are springs around the state, but there's some part of the state that don't have very many springs. But that's, we have a lot of nice springs in Wisconsin. And if you're interested in springs, that website from the survey that I mentioned, we have a nice page there where you can look for springs and look for data. We also have a lot of artesian wells and flowing springs. And in fact, Waukesha, you may know, is sometimes called the Spring City, or it was nicknamed Spring City because it historically had springs that were used as a spa for people's health. And it was even known as the Saratoga of the Midwest. And after Saratoga Springs, New York, Saratoga Springs, New York is a place that has a lot of natural flowing springs, and they had some health institutes there and sanitariums that used that water. Waukesha also had places like that. People traveled long distances to enjoy spring water there. There were bottling plants and so forth. And so these were some old postcards of the springs in Waukesha. Unfortunately, most of those, or just about all of them, are gone now. They've been covered by urbanizing, or pumping of the deep aquifer there has dried them up. There are also springs in western Wisconsin, though, and artesian wells. So let me talk a little bit about artesian wells. Artesian well is a well a flowing artesian well is a well that flows naturally like this. This is a well at Villa Louis down at Prairie du Chien. But artesian means a well that's involving, related to, or supplied by the upward movement of water under hydrostatic pressure in rocks or unconsolidated material beneath the Earth's surface. It comes from the French artesian, or from Artois, a region of France where they have a lot of wells like this in the 18th century. So that's where the word artesian comes from. How do they work? Well, again, let's look at aquifers. Here we have an upper aquifer, an aquitard, a lower aquifer, and a water table. And you can see in a water table well, it's called a water table well because when you drill that well, the water in the well, if you measured it from the top, stands at the water table. In an artesian well, though, the water in the well doesn't stand at the water table, it stands above the water table because there's pressure. There's more pressure down here than there is up here, and the water wants to move up that pipe. But it's not flowing. So this is an artesian well, but it's not a flowing well because the water's not flowing out. But if we locate that well down here, down slope, perhaps near the river or lake, and we have the top of it below this line, which is the pressure surface of the lower aquifer, then the water naturally flows out, and that's called a flowing artesian well. And we have some spectacular examples of those in Wisconsin. So in a flowing artesian well, the water in the well rises above the land surface and the well flows naturally, which for a hydrogeologist is a pretty cool thing. And again, how high can it rise? It can rise to the level of this pressure. And where did that pressure come from? Well, that pressure came from recharge at some higher elevation, some distance, as shown here. So here again is your flowing artesian well, and the water is coming through an aquifer that's getting recharged up here on a higher point on the landscape. And so that pressure, that elevation that just came from the rain falling there, that pressure is transferred down through the aquifer, and then it's released when you drill the well into it. So here, there are some famous artesian wells in Wisconsin. Here's a famous one at De Pere, up just south of Green Bay. This is a picture from 1890, and you can see this is the water flowing up to that level. People standing here in their raincoats. So this was a well in downtown De Pere. This is a little map by Weidman and Schultz, an old survey map published in 1915 that showed the locations of many of these artesian wells. So there were a number of these in the Green Bay and Milwaukee area even. Most of them now would no longer flow because there's been so much water use over there. There was also a lot of wells around in this part of the state. And so Weidman and Schultz in their book back in 1915 said flowing wells are common along the valley bottoms of the Mississippi and the Wisconsin, and also many of the side valleys leading from these main streams. These flowing artesian wells get their supply from the upper Cambrian sandstone. And so all these little blue dots are wells that they were mapping back in 1915, flowing artesian wells, including a lot along the Kickapoo River. And this was the cover of their book, and there was a very famous well that I talked about the other day that Gillian heard me talk about at Prairie du Chien, a famous well that we call the library well because it was drilled at the Prairie du Chien Library that was only abandoned a few years ago. But it used to flow 60 feet in the air, and I just like this lithograph of the how people celebrated this kind of thing. This was the park at Prairie du Chien back in 1882 or something, showing that it was the centerpiece for a city park, this flowing well. And not only was it used for water supply, but they actually powered a mill with the pressure from this well. So groundwater was not only used for water supply, but it was used for power in some cases. Unfortunately, when you do this, you're releasing pressure from the aquifer, and eventually all these wells, the pressure goes away and they stop flowing. So let's switch topics now to groundwater quality concerns. And I know many of you are maybe here because of groundwater quality concerns. I don't have time tonight to talk about get into detail about these things, but the things that we worry about, that I've worried about in my career are first of all, pathogens, things that make people sick. Bacteria, viruses, protozoa that are often related to fecal waste or livestock waste. We have seen these many, many shallow wells and in some deep confined aquifer wells as well. Nitrate. Nitrate is a huge problem in Wisconsin. Nitrate is probably the most widespread groundwater contaminant, largely related to agriculture here, from nitrate fertilizer, but there's also human sources and animal sources from septic, of course. But nitrate is a very, very widespread contaminant. It has a fairly low health standards of 10 parts per million, which is exceeded in hundreds or thousands of wells are exceeding that, and it's very hard to get rid of. So that's a big problem for us. We have things like arsenic, which are naturally occurring elements that obviously you don't want to be drinking, but they can be mobilized. They're naturally occurring, but they can be mobilized when we drill wells and we start pumping water. We can make these things mobile. Pesticides and ag chemicals, things like atrazine or other agricultural products are a big issue, as are radionuclides, which are naturally occurring at low levels, but in deep wells, mostly in northern or eastern Wisconsin, but even around here in some deep wells, natural radium and uranium and radioactivity can be a problem. PFAS, which are the kind of the contaminant of the day, they're man-made chemicals that are used in a lot of things like waterproofing and fire retardants. Those have been showing up in multiple sites in Wisconsin, and the problem with those is that they were made to be very resilient chemicals, which for the purposes that they were made for, but being very resilient means that they're very hard to get rid of once they get into groundwater, and they seem to be turning up in groundwater all the time, and the health effects are not really widely understood. And then there are a lot of other emerging contaminants, things like pharmaceutical compounds, drugs in the water, PCPs, which are personal care products, your perfumes, soaps, skin cream, whatever goes down the toilet or down the drain ends up in groundwater. So there's a whole mess of things, generally from wastewater or solid waste sources. So as I said, later on, if you want, we can talk about some of these things. I don't have time to go into all of them. If you want to get into some detail, the legislature and the Groundwater Coordinating Council in Wisconsin, which I used to be a member of, does a report to the legislature every year about groundwater, and this is a publicly available report that's got a lot of detail about all these subjects. So that's a good place to get more information very easily, and you can get that off the DNR website, and it's quite comprehensive. Susceptibility to contamination. This is a map that I actually helped work on many years ago that just shows in general the susceptibility of shallow groundwater to contamination in Wisconsin. And it's based on major things like depth to bedrock, type of superficial material, type of soil, depth to the water table. And basically, the more red it is, the more susceptible to contamination. The more green it is, the less susceptible. And it's just an educational product, but it does show you some things. For example, where are the very susceptible areas? Well, you've got Door County here where you have shallow fractured bedrock, not much soil on it, and very susceptible. Central Wisconsin where you have sandy soils, again, very permeable, shallow water table. You've got down here, you've got particularly these uplands where you don't have a lot of soil. You've got some karst features and shallow bedrock. Lots of parts of northern Wisconsin where you have, again, sandy soils over fractured rock. On the other hand, places that are less susceptible along Lake Michigan, where you have got like clay deposits and some deeper groundwater there. This basin here, again, a lot of clay deposits as you have up in here. So just in general, this is for educational material to help people understand the relative susceptibility of different areas for groundwater contamination. But a particular area that we think about a lot are these karst features, or shallow fractured bedrock features. And so when we're talking about karst, we're talking about fractures and cavities that are widened or opened by solution in carbonate rocks like limestone or dolomite, of which we have a lot in these upper Paleozoic rocks and in the Silurian rocks in eastern Wisconsin. And so a karst landscape can look something like this, where you've got some little sinks or sinkholes. You've got fractures here. Below the surface, you've got a lot of openings, and water can move very quickly through these things with very little filtration or attenuation of contaminants. You can have caves. Often you have springs. Where do we expect to find those? Well, this is a map of shallow carbonate rock. So we take the type of rock, and then we look at the depth to the top of that rock, and we've got two categories, 0 to 50 in the darker orange and greater than 50 in the lighter color. And so these are areas that, as a hydrogeologist, I view as pretty susceptible to surface contamination from surface sources. And so, it covers a pretty big swath of the state here around that dome that I talked about before. And and you guys have seen around here features like this. This is a sinkhole near Blue Mounds. This is a conduit and a road cut along 151. Here are some cave photos, and I know all of you can find places like that where groundwater is going to move very rapidly with very little attenuation. So this brings me to something I wanted to mention that we just finished called the SWIG study, or the Southwest Wisconsin Geology and Groundwater Study, which was a multi-year study that we just wrapped up, colleagues and I wrapped up just a couple of months ago. It was a big study, and I don't have time to talk much about it other than to just tell you about it. It was an examination of groundwater quality, well water quality in Grant, Iowa, and Lafayette counties. It ran from 2018 through this year. It was supposed to be a little shorter, but COVID got in the way and made it a little longer. And basically what we were looking for was to see, first of all, to see what was the ambient groundwater quality in these three counties, and then what were the sources of contaminants. And we're basically looking at nitrate and bacteria or pathogens. And so we were looking at things like well characteristics, rainfall, land use, septic systems, groundwater situations and recharge, and geology, and with respect to nitrate, coliforms, wastewater, and manure. It was a big study, probably one of the biggest of its kind ever done, because we sampled over 840 wells. A lot of statistics were done to compare the results to well construction and land use factors, and there's a big long report that you can get from the Iowa County Extension Office. Again, so I don't have time to talk about all the results, except to say that one interesting thing to me was here's a map of Grant, Iowa, and Lafayette counties, and the red spots are wells that were positive for total coliforms or had high nitrate, that is nitrate over 10. An interesting thing to me is that it's pretty well distributed. In other words, there's not a hot spot where you can say, oh, this area is really contaminated and that area isn't. It's pretty uniform, okay? And I found that very interesting. So you can't just blame this on one source somewhere. This is whatever the source is, it's pretty widely distributed. And then just some of the key findings is that what we did is back in 2018, 2019, we did these synoptic or wells sampled at the same time. We found 42% of the wells in November and 27% of the wells in April were positive for total coliform or had high nitrate. So those are pretty big numbers of wells that you really shouldn't be drinking from. We found that human wastewater and livestock manure are both contributing to private well contamination. Human wastewater was more common as livestock manure. We found pathogenic genes, in other words, genetic material indicating things that would make you sick in the 66 wells. And these, again, had material from both animal and human sources. We found that contamination could be statistically related to numerous well construction and land use factors. All this is enumerated in many pages in that report. So again, I'll point you to the report if you want to learn more about that. If you want to learn more about water quality, there's an excellent water quality viewer that UW-Stevens Point has. You can get, it's free, just go to this website or just Google Stevens Point Well Water Quality Viewer, and you can get a map of the state, and you can look at a number of different groundwater constituents and get maps like this of your county or your section or your township for many of these things. And these are all based on private well samples that have been analyzed over the years by the UW-Stevens Point laboratory. So I often refer people to this website when they ask about groundwater quality. Now let's spend a couple of minutes on groundwater use. We use a lot of groundwater. About 207 billion gallons a year are pumped out of wells. And that's a lot of water. And this map, which I got from the DNR, just shows you where all these wells are. These are high capacity wells. And the thing that really stands out is the irrigation wells, which are green. Look how many irrigation wells there are in central Wisconsin, along the river valleys, in other places. So the green are irrigation wells. Blue are municipal water supplies, so city wells. And so there's a cluster around Madison and Waukesha and Green Bay, various La Crosse. The cities have their wells. The other ones, the orange ones, are industrial or ag dairy wells. And then there are parts of the state where there are very few high capacity wells. So you can just see that water use varies from place to place. But you can imagine there are some consequences of this water use. And so we call these the quantity concerns. When we do a lot of pumping, it causes two things: drawdown or lowering of the water table or water levels near the well, and reduction of groundwater flow to surface water. I mentioned that surface water and groundwater are well protected, so are well connected. But if you start pumping a lot of groundwater, you're going to impact a stream, and we've certainly seen that happen. So the idea here is that when you pump a well, you have this cone of depression of the lowering of the water table around the well. If you have wells pumping nearby at the same time, those effects add together, or they're called cumulative. So these are called cumulative impacts. And so the more wells you have nearby, all the wells are impacting the water table and actually impacting each other. And as an example, here's the cumulative impact at Madison. So these are wells around Madison. Here are the Madison Lakes, if you wanted to get oriented. This is the shallow water table aquifer, the deep aquifer, and you can just see there's each pink spot is a municipal well. But you can see that there's kind of this large cone of depression that's really the cumulative impact of all these wells together around central Madison. And it's interesting, in Dane County, it's in the center of the county because that's where all the wells are. One of the issues that we worked a lot with in the last few years is in the central sands, where you have all these high-capacity wells. So this is a map of central Wisconsin, so I think Stevens Point's about here, and each of these dots is a high-capacity irrigation well. And over the years, we've got, back in the 1960s, there were hardly any, and by 2010, there were over 1,500 high-capacity irrigation wells in that part of the state. These are having a cumulative impact, and there's been a lot of concern about that. And the kind of the poster child for this was the Little Plover River study that I worked on a few years ago. Little Plover River is a small river up near Stevens Point, and it historically was a trout fishery, but back in the in the early 2000 teens, it actually dried up for the first time in known history. Why did it dry up? Well, there was a lot of thought that it must have something to do with these irrigation wells, but it was hard to prove that. So we did a lot of modeling. We did a lot of computer modeling, and these slides kind of summarize what we found. That this was a model that we did of the capture zone for this river. So the river itself would be about in here. You probably can't see that well from where you are, but the river is about here. But the blue area is the groundwater shed, or the capture area for that river. So this is where the water would have been coming from if none of these wells, which are the little brown spots, existed. So we turn all those wells off in the model, and this is where the water would have been coming from. We turn those wells on, and now is this is what it looks like. And you can see it's kind of weird looking because it has these fingers, because each of these wells is basically stealing the water or diverting the water that would have gotten to the river. And so right there you can see that there's less water coming to the river, so of course there's less flow now. And that was pretty convincing to people to see this kind of thing. Of course, we have a lot of statistics and numbers to back this up. There was also a lot of concern about lakes in central Wisconsin. So in 2021, the DNR and our survey and the U.S. Geological Survey did a big study of lakes in the central sands to see if pumping was impacting those lakes. Again, this was hard to do because, you know, what impacts a lake? Well, pumping is one thing, but we have climate change going on, we have weather going on, different rainfalls going on. But they did find that the irrigating agriculture was not drying lakes up, but it was lowering the water level in some of the lakes they studied. So, and that was a pretty robust piece of work. So that gets us to a little bit about water law. And how do we approve high-capacity wells in Wisconsin? What is a high-capacity well? First of all, it's a well that can produce 70 gallons a minute, which is 100,000 gallons a day or more. And so if you're not going to produce that much, you don't need a permit. But if you're going to produce that much, you need a well permit. And keep in mind, a lot of these wells are, you know, they might be producing 1,000 gallons a minute, so way more. So when the DNR is reviewing a high-capacity application, they have to look at all these things about, is it in a groundwater protection area, which means is it near a trout stream? Is there water loss, meaning is it going to go to a bottling company or being taken out of state somehow or out of the watershed? Is it going to degrade the water resource or cause significant adverse environmental impact, which is kind of a subjective thing? And is it going to have cumulative impacts on other wells? And so that's what they do when they're reviewing these applications. But over the last decade, there's been a lot of controversy about what that actually means. And this goes back to what's called the Lake Beulah decision, which was back from 2011, a Wisconsin Supreme Court decision where, and Lake Beulah is a little lake over in Waukesha County, near the village of East Troy. And the village of East Troy wanted to drill a new well to supply their village. And the lake owners around Lake Beulah were worried that this well was going to impact their lake. And the DNR at that time said, well, we have no authority about this. We can't, you know, we can't do anything about that. We have no authority. And so the Lake Beulah property owners sued the DNR, and they won in the Supreme Court, which found that not only did the DNR have authority, they had an obligation to figure this out, to see if the well was going to impact the lake. And that made the DNR start doing a lot more review of well permits. But it got complicated. So this lake, what was called the Lake Beulah decision, which as a hydrogeologist I thought was a good positive decision, happened in 2011. But then we had a change in politics got in there, and we had a change in the governor's office, and the attorney general decided that the DNR did not have authority to consider these impacts. And so that forced the DNR to stop evaluating these impacts. And so that, and a lot of wells started getting approved But of course, there were a lot of lawsuits from various environmental groups, and they challenged these permits granted. A judge threw out the permits, and the DNR sued back. Interesting, the DNR leadership and the DNR staff were basically on opposite sides of the fence here. In 2020, we have a new Attorney General who reverses the previous opinion, and the DNR must now consider cumulative impacts. And so in 2021, when I made this slide, and now the DNR is currently evaluating cumulative impacts. But who knows? If we have a change in the governor's office, this might change back. So just to point out that these things are fluid. These regulations are not set in stone, and they can change. And so this was one of the couple of the headlines from the last thing that happened when the Attorney General decided to change back to having these reviews. So I'll finish up there, and just to summarize, we've got a complicated or complex and rich geology in Wisconsin that governs our groundwater resources. We have great aquifers here. We have great groundwater here. There are some areas of scarcity and some areas of water quality problems, but overall we have quite a wonderful resource here. And we have there are some threats and local issues, and it's complicated, but it's, having worked in other places of the world and seen other places, we are rich with groundwater, and it's a wonderful resource that I don't think people take for granted here. There are countries and states that would kill to have the water we have, and so it's really something to protect. So I will stop there, thank you, and answer any questions that you have. Yeah, Gillian.
So that slide that you showed, I think it was an image from the DNR, and it said the susceptibility to contamination. How do they arrive at that? Is that just based on the number of tests?
Oh, the map with all the colors on it?
Yeah.
Well, I can tell you, because I worked on that years ago, and it was, at the time, they were looking for just a general idea of what parts of the state were more susceptible than others. And so we did a lot of talking about, well, what would make things susceptible? And you think, well, permeable soils are more susceptible than clay. Shallow groundwater is more susceptible than deep. And fractured bedrock is more susceptible than porous. So we put, there was quite a committee, and we did a lot of thinking about that. And then we assembled data sets from all these parameters, and then kind of put them together in at that time, GIS wasn't invented yet, so this was a very complicated process that could be done a lot easier these days. But it was sort of semi-quantitative, and again, I always want to point out it was just done as a kind of a public education thing. It's not something that we didn't want people to try to find their house, or or something like, or their property. We just want to give people a general idea, and the general idea is that a lot of the state is fairly susceptible, and so that's one message.
I just always see that. And I may be confusing which map I'm thinking about, but Crawford County, so for instance, Vernon County and Richland, were one color, and Crawford is a lighter color, and I'm going, how are they different?
Well, I'd have to go back and study it.
Yeah, okay, it just doesn't really make sense.
Okay, well, yeah, maybe not. Anybody else? Thank you for putting up with that and listening to me. Yes, sir.
Are there any cases where maybe a more shallow well, maybe above an impermeable layer, could actually, be pulling out pollutants before they permeate further?
Oh, sure, that can happen. Yeah, I mean, one of the advantages of having a permeable place is that it is possible to pump out the pollutants. That's one remediation strategy. It's called pump and treat. That means you have to do something with the water, but yeah, it's possible that you can cleanse an aquifer by pumping out. Some things, that works better with some things than others. For instance, nitrate, the nitrate problem I said is a terrible problem. We could solve it though if we would stop using nitrate. Nitrate is mobile, it moves with groundwater. And if we turned off the source in a few years, most of the nitrate would be gone. Of course, it would go into the Mississippi River and it'd be a problem somewhere else, but it would get out of the groundwater. But something like PFAS or a lot of organic chemicals which are not so mobile are much harder to get out because they tend to stick to the soil particles or the sand and gravel and be harder to remove. Yes, sir.
What would be examples of PFAS? What would be sources of them?
Well, the biggest one are one of the big ones are airport like de-icing compounds and fire retardants. And I'm not sure how fire retardants work, but they're apparently quite a big source has been airports where they sprayed this stuff around and then it ran off the runways and soaked into the ground. And so most of the airports in Wisconsin have a PFAS problem. But I understand they're also used in things like Gore-Tex and Teflon pans and non-stick utensils and raincoats and waterproofing for your car seats and lots of stuff. So they're a pretty ubiquitous thing. Like a lot of chemicals, I said it's sort of the pollutant of the day because it's 10 years ago no one ever heard of PFAS. And that doesn't mean they weren't here, it wasn't around, and nobody was analyzing for it, or they didn't know how to detect it, or they didn't know how to detect it in the tiny quantities that they are now. And I'm sure in the next few years we'll find something else like that. It's one of the interesting things about my career is we discover something like, oh, there's pesticides in the water, it's a crisis. And I think, well, the pesticides were probably there 5 years ago too. we just didn't know it. So, it might be a crisis, but it's not like it just happened. It's been there. Yeah, go ahead.
If global warming proceeds kind of at the pace that some of these models of prediction, of the impacts of global warming occur, what will be the impact of global warming on our water table here in Wisconsin?
Well, that's a great question and one that's been hard to answer, and because we've tried a little bit. You may have heard of the Wisconsin Institute on Climate Change Impacts, it's called the Wisconsin Wiki, and they've done some predictive modeling of what the weather will be, and there's the warming aspect, but then there's also what will happen with precipitation. Unfortunately, the models they're not very consistent. I mean, depending on which model you use, you may get a lot more rain or a lot less rain, or the same amount of rain, but it's focused in, more intense. Most people think it'll be maybe about the same amount of precipitation, but it's coming in more intense. You'll have intense rain, and then you'll have intense drought, and then intense rain. So it'll be less consistent than it is now. And we've modeled that, and again, depending on which of those models you choose, you can get different results. So I can't tell you right now what the answer will be because the models are not consistent about what will actually happen to the water resources. We know it's going to get warmer, but how that'll affect rainfall and recharge is not so clear to me. Anyone else? Yes, sir.
Just wondering, you had a slide in the wells around Madison. How deep is that cone of depression?
Well, around Madison, in the deep aquifer, it's something like 60 feet, which is not a lot. And that's because you have the lakes right there, and the lakes are actually losing water. They're helping recharge. It's interesting that if you go over to Waukesha County, the cone of depression, or the decline in the deep head has been something like 500 feet. And that's because you have the shale called the Makokata Shale over there that's over that aquifer and doesn't allow much recharge. So, and yet the amount of pumping is about the same. So it just shows you the geology makes a big difference.